Hello everyone, my name is Malik Arslan Nisar and I'm a TA for this course Numerical Linear Algebra. So this is a pre-recorded session for week 8 because the live interactive session which I took earlier, the video file got corrupted somehow and so I could not be able to upload it on YouTube. So this is sort of a backup video for that. I'll be uploading it on my YouTube channel in the playlist numerical linear algebra. So the duration of this video is going to be lesser than the original duration, which was nearly of 2 hours. So this will be a lesser duration because I have the notes with me of the live interactive session. So it will take less time, and obviously it's a pre-recorded session, so there won't be any interaction, and the duration is shorter. But I'll try to cover all the questions which were discussed in the tutorial. So I think we should start now. Okay, so this is the first question. Since the week 8 was mostly based on condition number and stability of matrices and the perturbation matrix, perturbation theorem and residual theorem, etc. So the questions would be revolving around that only. This is the previous year assignment for the course, previous year assignment of week 8. So the first question is that we have been given a matrix G with entries 2, 4, -1, 2, 5, 2, -1, -1 and -1. Now we have to calculate the K1 of G, that is the K1 condition number of G. Okay. Now we know that the one norm condition number is equal to the one norm of G into the one norm of G inverse. So one norm we already know how to calculate. We can just by observation from this matrix we can calculate the one norm. So we will first, and similarly for G inverse also we can do that. So first we calculate G inverse, and you know how to calculate G inverse. It's simply adjoint of A upon determinant of A. I'll not show you how to do it because we have done it in subsequent in the previous videos. You have done it many times. And when we calculate the inverse it for this matrix, it is coming out to be this. And the one norm of G, we know that the one norm is nothing but the sum of the maximum among the absolute sum of the columns. Absolute sum means that for each entry you have to take the absolute value and add for each column, and the maximum column sum will be the one norm. As in this video it's 2, for first column the maximum sum is going to the absolute sum is 2 plus 2 plus 1. Okay, we ignore the sign, so it's 5. For the second column it's 4 plus 5 plus 1, that is 10, and for the third column it's 1 plus 2 plus 1, so that is 4. So maximum among these is for the second column, that is equal to 10. Okay, and that is going to be the one norm for G. Similarly for G inverse, one norm is calculated. It is easily observable that for the last column the entries are greater than others, so that is going to be the uh, one norm for G inverse. So we add the absolute values of these entries and we get 2.33, which you can cross verify also. It is the maximum sum among other entries. So condition number K1 is simply norm of G1, one norm of G and one norm into one norm of G inverse. So it is simply 23.3. Now moving to the second questions, we have been given a set of statements. Okay, there are 6 statements and you have to check whether they are correct or not. So the first statement here is condition number of AB is less or equal to condition number of A into condition number of B. So for checking this, we proceed with the left hand side and you can see that condition number of AB is nothing but norm of AB into norm of AB inverse. Okay, And we know that norm of AB into norm of AB inverse is always going to be less or equal to norm of A into norm of B into norm of B inverse into norm of A inverse. Okay, you know this norm. And from here you can see, just by rearranging, we can see norm of A into norm of A inverse is nothing but condition number of A, and norm of B into norm of B inverse is nothing but condition number of B. So it is K into KB. Order doesn't matter here because norm is just a number, it's not any matrix or anything, so order doesn't matter here. So clearly you can see that yes, condition number of A, we started from right hand side and we ended at left hand side. So this statement is correct. Condition number of AB is less than condition number of A into condition number of B. So now the second statement is that K2 of UAV is equal to K2 of A. That is the condition number of UAV is equal to condition number of A, where U and A are orthogonal matrices. Okay. Now for checking this statement, we know that K2 of UAV is equal to norm of UAV, 2 norm of UAV into 2 norm of UAV inverse. Okay. Now when we take the UAV inverse here, we know that it's going to be V inverse, A inverse, U inverse, right? And since U and V are orthogonal matrices, we can simply write as V transpose A inverse and U transpose, right? Now, yeah, so simply, yeah, V transpose A inverse U transpose. The norm of this is also going to be, if norm of UAV is going to be norm of A to norm of A, then norm of, because we know that is there, that U into A into V ka 2 norm is equal to 2 norm of A, if these are the orthogonal matrices. So similarly will apply to A inverse, because V inverse and U inverse or V transpose U transpose, simply they are also going to be orthogonal. So this is also going to be 2 norm of A inverse. So now 2 norm of A into 2 norm of A inverse is nothing but condition number of K2 of A. Okay, so that is how we prove the second statement. Yeah, yeah, it is also correct. Now for the third statement, it has been given that condition number of A is less or equal to 1. Okay, so let us check this. We know that um, okay, we know that we can simply write 1 as what, A into A inverse ka norm. Okay, that will be norm of what, norm of an identity matrix, and that will be equal to 1 only. Okay, now here condition number of A implies what, condition number of A implies that it is norm of A into norm of A inverse. Okay, now we know that norm of A into norm of A inverse is going to be definitely greater than what, norm of A into norm of A inverse, right? As we saw in previously also. So if this thing is greater than this, then we know that norm of A into norm of A inverse is greater or equal to norm of A into norm of A inverse, which is nothing but what, 1. So condition number of A is greater or equal to 1. Okay. So here it has been mentioned otherwise. Okay. It has been mentioned otherwise. So this statement is wrong. Now the fourth statement has been given as that condition number of alpha A is equal to condition number of A, where alpha is any scalar. So we will just expand the left hand side, and we can see that the condition number of alpha A implies nothing but norm of alpha A into norm of alpha A inverse. And norm of alpha A, we will simply take alpha outside and then in multiplied with norm of A, and in case of this alpha into A inverse, we will simply take 1 upon alpha outside, and it will be norm of A inverse. Alpha and alpha goes, and it is norm of A into norm of A inverse, which is nothing but condition number of A. So this statement is also correct. Now for the fifth statement we have been given as condition K2 of A, okay, condition number of A is less or equal to condition number of A transpose, okay, K2. You have to see for K2. So, the condition number of A is what? 2 norm of A into 2 norm of A inverse. You have to keep in mind that you have to, if it is given K2, then it means that the norm associated with it is going to be 2 norm. If it's K1, then you have to consider 1 norm. If it's K infinity, then you have to consider infinity norm, okay? You cannot do otherwise. So for K2 of A, we know that it's again norm of A into norm of A inverse. When I say norm, it means 2 norm. Now K2 of A transpose will be what? Again norm of A transpose into norm of A transpose inverse. Now for the A transpose, 2 norm is equal to what? 2 norm is going to be the under root of a maximum of the eigenvalues of A, and which are not going to change in case of A transpose. So it will be same as A, and same goes with A transpose. Again it will be similar as A, so you can write it as 2 norm of A into 2 norm of A inverse. So yeah, the condition number K2 of A transpose is equal to K2 of A, and here it has been, yeah, in the statement it has been given otherwise, that it's less, so the statement is wrong, but this thing is correct, that K2 of A is equal to K2 of A transpose, okay. Now for K1 of A transpose is equal to K infinity of A, we know that K1 is what? K1 is the maximum among the column sum, right? As we saw in the first question also. And K infinity is what? The maximum among the row sums. Now maximum of row sum for A is equal to K infinity, right? K infinity of A. And maximum of column sum of A transpose is equal to K1 of A transpose. Now, we know that the rows and columns get interchanged while we are doing the transpose. So, the rows of A will be similar, like the rows of A will be the columns of A transpose. Therefore, the condition number K infinity for A, okay, that is the maximum row sum, will be equal to the maximum among the column sum of A transpose. So, this statement is also correct. Okay. Now, moving to the next question, the condition number K2 of A for a given matrix A, okay, we have been given a matrix, it and we have to find its K2, okay, condition number. So, you can see here that it is a symmetric matrix, so A transpose is equal to A. Now, 2 norm of A, we know it's under root of maximum of eigenvalues of A transpose A, or you can say singular values of A. Maximum of the singular values of A, or maximum of eigenvalues of A transpose A. So we have to calculate the eigenvalues of A transpose A. Now, since A transpose A is a symmetric matrix, A transpose is equal to A. So we will calculate the maximum of eigenvalues of A square. Okay, and we know that for calculating the eigenvalues of A square, we can simply calculate the eigenvalues of A, and then we can take their square, and that will be the eigenvalues of A square, right? So we will calculate the eigenvalues of A. You know, it's very simple. Just we have to solve the characteristic equation, okay. I'll write it here. You write A minus lambda I is equal to 0, right? After solving this equation, after implementing, yeah, and sorry, you take its determinant to be equal to 0, okay. So from here you reach at this 2 minus lambda 2 4 2 5 minus lambda 8 4 8 and 17 minus lambda. And when you solve this, okay, It's very simple, you know how to do it, and I have just written the final characteristic equation after simplifying. So the factors for that equation are lambda minus 1 square into lambda minus 22 is equal to 0, from which we get lambda, the eigenvalues, okay, the three eigenvalues for this matrix equal to 1, 1 and 22. Okay. Similarly, the eigenvalues of a square will be what? Equal to 1, 1 and 4, 8, 4. Okay. So, the condition number of A, yeah, so here, now we know that condition number K2 of A, apart from writing it as norm of A 2 into norm of A inverse, we know that it is equal to under root of maximum of the eigenvalues of A transpose or A. Okay, that is the, here I have not written it. It is, if we are taking the eigenvalues of A, then we have to write lambda max upon lambda min. But if you are taking the eigenvalues of A transpose A, it will be simply equal to under root of max of eigenvalues of A transpose A. So that is what I have written here. Okay. So the maximum among the eigenvalues of A transpose A is this 484. So I'll simply take its root, which will be equal to 22. So this is the K2 for A. Okay. Now moving to the next question. We have been given a linear system Ax is equal to B. Okay, where the matrix A has been given and it is equal to, it's a 2 cross 2 matrix and the entries are 2.001, 5, 5, 5, 2 and 5. And we have been given B also, okay, equal to 5 and 5. So we have to basically find the solution for this system. No, sorry. This is the linear system which has been given and we have to find the solution of the system A plus delta A. So there are certain perturbations in this system, okay. A plus delta A into x plus delta x is equal to B plus delta B, and delta A and delta B have been given to us, okay. So the solution for this system is x plus delta x, okay. Now how do we solve this system? It's simply that like we follow any normal linear system, Ax is equal to B as x is equal to A inverse B. Similarly, we will do here. Here also x plus delta x will be nothing but A plus delta A inverse into B plus delta B. A plus delta A we can simply calculate. We will just add the matrix A with delta A and we arrive at this matrix, okay. 2, 5, 2 and 5.001, and we take its inverse and multiply it with B plus delta B. Now the calculating the inverse of a 2 cross 2 matrix is very simple. You will just exchange these two entries and you will put a minus sign here and divide it with its determinant. So that is how what I have done here. And after solving this system, okay, when you multiply these matrices with this this matrix with this vector, you get something like this, okay, minus 5.001 into 10 to the power minus 3, and the second entry is 4 into 10 to the power minus 3. You can simply check it, you'll just know how to multiply a matrix with a vector. And after doing this is basically our solution, okay. So x plus delta x is equal to 2.5005 and 2, okay. Now one thing here you can do, that you can on your own also check that what is the solution for this system, okay, and calculate the value of x, and then you can compare x and x plus delta x, so that you can see that how much the perturbations in A and B affect the solution, okay. Now we can move to the next question. So here also a matrix A has been given. We have to find the 2 norm of the matrix, that is again lambda max of A transpose A. Now how to find A transpose A? Obviously you will take the transpose of this matrix, multiply with it, and it's just multiplication between two 3 cross 3 matrices, and after doing it you will get the value of A transpose A. It's equal to 14, 25, 18, 25, 98, 93, 18, 93, and 129. Now you will calculate the eigenvalues for this matrix. Okay, so yeah, the characteristic equation, again you know how to write it. Okay, it will be uh, A transpose A minus lambda I. Okay, determinant is equal to 0. So here when you proceed, you get this matrix lambda for matrix A transpose A will be 14 minus lambda 25, 18, 25, 98 minus lambda 93, 18, 93, 129 minus lambda. And this is how I have simplified it. Okay, this entry into the determinant of this minor. Okay, then similarly plus 25, sorry, minus 25 into the this minor. Okay, which I have done here, and then plus 18 into the determinant of this minor, which is 25 into 93 minus 18 into 98 minus lambda. Similarly in other two also we do in the same way. Now as you simplify this equation, the final equation which we arrive at, the characteristic equation, is this: minus lambda cube plus 241 lambda square minus 6222 lambda plus 27225. Okay, this is the equation we are arriving at. And since it's a cubic equation, you can simply solve it in any scientific calculator and you will get the values of lambda. I have done that already here. Okay, and now for finding the 2 norm, we know the maximum among these eigenvalues ka root we have to take. So that is going to be this 212.2959. Okay, when we take its root, it is coming out to be 14.57, which is the correct answer, which is the basically the norm of A, 2 norm of A. Now in extension of this question, you have to find the condition number of A. That is again, condition number is going to be under root of lambda max upon lambda min. Okay, which is going to be 212.2959 upon 5.5350. Okay, and that is going to be 6.1931. Okay,